All right. So number 3. Took us back to our two-way tables and our joint frequencies and our relative frequencies, conditional frequencies. Okay, are we good?
How do you do D and E?
How do you do D and E? It's a relative. B?
Yeah.
What percent of those who bring a tablet, so this is our condition, those who bring a tablet also have a smartphone. So we're only looking at the tablet column.
Alright.
So also have a smartphone is 57 out of 70.
And same thing with D?
Yep. That's how you do it. So this time the condition is has a smartphone. So we would be looking at just this row. Okay, let's go ahead. Anything else? All right. So this one, did you call it somewhat symmetric?
Yes.
If we folded it down here, it would be somewhat symmetric, except for that one little piece right there. So, can we determine using the 1.5 IQR rule if that is an outlier? No. We don't have enough information to determine that. What we could do is go back and use the midpoints of all of these and list the data that way. The midpoint of the bin is the piece of data that's halfway in between. So we could say, what's this first bin? 15 to 19? So the midpoint would be 17. We could say there are 5 17ths. And then the midpoint of this bin is the second one 20 to 24? I'm looking at it at a very,
Yes.
okay, good. So we could say there are 6 22s. And we could list out all the data this way. Do you see what I'm doing? And then we could determine if this were an outlier. But right now, let's just call it a possible outlier. We can say it looks like an extreme value. We can say it's a possible outlier. But not without testing could we say it is definitely an outlier. Okay, and then number 5 just asks you to give some quantitative and categorical. So quantitative, those are our measurable variables, things that we can measure: height, weight, scores, times, things measurable. Categorical, those are things that are countable. How many red shirts are in the drawer? Sizes, those different things. Divide into categories. Yes, sir? Zip code, yep. Even though it's a number, it categorizes. I live in the 30276. Are y'all 30215? Oh, 30269. Okay. All right. So yesterday we determined that using the 1.5 IQR rule, that 0 was not an outlier. So our dot plot should have looked like this. And we could have called this skewed left. But if we said it was, and we dropped it as an outlier, then our dot plot would look like this. I still think it's somewhat skewed left. Now, here are the mean, median, and modes with 0 and without 0. Did the median change?
No.
Did the mode change? But when we drop an extreme value, what does change? The median. So this is just more proof that extreme values tend to skew the mean. Move the mean. So if we drop those extreme values, which you will in a data set, then you wouldn't even look at it.
Would it be considered an outlier if you had like a bunch of data on the really high side and a bunch of data on the really low side and one in the middle?
That would be some terrible data. That data would not be very helpful if all of it was at one end and all of it at the other. I wonder what that would tell you. Maybe you ask a room full of Democrats a question and a room full of Republicans a question, so all of them answered at one end and all of those answered at one end.
Then you ask the president.
And then
you ask the host.
so sometimes that data is not helpful at all. It's very biased. Okay. Number 8, we call it bimodal because it has 2 peaks. Therefore, it has 2 modes. It has 2 modes, we call it bimodal. And number 9, A was Magdalene and B was Peter. Huh. It just hit me. It didn't hit me when I did the problem. Okay.
Peter.
Alright. Alright, today we're going to look at scatter plots. So if you have your workbooks with you, open to page 345. If you don't, it's alright. You can work along
I remember
with
doing these last year. These were really easy.
Okay, so I like what Ian said. I remember doing these from last year. So we're already familiar with scatter plots. We know that scatter plots are just a collection of ordered pairs. And when we graph them, sometimes it can just look like a bunch of dots. Okay? Now, sometimes the dots form a shape. Now, if these dots kind of fall along a linear pattern that increases as one increases, the other increases, we call that a positive correlation. So if we create our scatter plot and it looks like this, we would call it a positive correlation. So that means that they are both going up and they are both related. So here's a real world example of a positive correlation. If we look at the age of a child and the child's height, so we're talking about children here, you'll find that as the child gets older, the child becomes taller. So as one variable increases, the other also increases. Now obviously there's a stopping point to this because I haven't grown any taller since 8th grade. So as one increases, the other increases. This is a positive correlation. A negative correlation exists when as one increases, like in this case, as the x increases, the y decreases. That gives us a negative correlation. So with a negative, as one is going up, the other is going down. And it makes this negative correlation, negative slope if we think in terms of a line. So a real world example for that would be the age of the car and the car's value. So as the age of the car increases, the value of the car decreases. And you may be thinking, but what about antiques? Well, this is pretty much a rule for a while. Like, my car is 9 years old and it still hasn't started appreciating yet. We're still depreciating. So yeah, maybe if my minivan hit like 400,000 miles, it would appreciate. What do you think?
What does that mean?
Doubtful.
Doubtful.
Like it was like.
What about like a,
Oh. Okay.
Yeah.
what about like a really expensive sports car?
A really expensive sports car. Most of them still decrease in value.
It depends on where it's from.
Like a Ferrari goes down, like it's like half its value. Like as soon as you start driving.
Most cars lose a good bit of value once you drive them off the lot.
You wait a bunch of years and it starts.
Okay, and then we have this. It's just everywhere, isn't it? There's no pattern. Very scattered. So when we have a scatter plot that looks like this, we can't really see any correlation. There's no correlation. We can't really define a relationship between the two variables. So in the other examples, we could. So a real world example of this would be like the shoe size of a baseball player and their batting average. Makes sense that those two things would not be correlated at all. There's not a relationship between the two. All right, so a positive relationship exists when both variables increase or both decrease at the same time. A negative relationship exists when one increases and the other variable decreases. Okay? All right, so which of these well, let's start this one. Any correlation here? No, no real correlation. Any correlation here?
No medicine relation.
No.
Cluster.
All right, what about C?
Yes.
Yes, a negative correlation. What about D?
No.
No. What about E? Yes. What about F?
Yes.
Yes. So what kind of correlation would C be?
Negative.
Negative correlation. So see if we kind of drew in this line, it does look like it's decreasing. Okay, what about this one? Positive. And what kind of line could I draw through this one? Horizontal. So this one would be positive, negative correlation. This one would be positive, and this horizontal we would describe as constant. Constant. Okay? Any questions about that? All right. So let's take a look at your text, your workbook now. And it kind of reiterates the same thing. So when we have two real-world variables are measured from the same things, you obtain a set of paired numerical data that you can plot as points in the coordinate plane to create a scatter plot. Sometimes the scatter plot will show a linear pattern. When it does, the linear pattern may be tight. Now when it talks about being tight, that means all the points are kind of close to the line. Or it may be loose, where they're further away. The degree to which the scatter plot shows a linear pattern indicates the strength, and we just talked about that. Strong linear correlation, or weak. So it denotes the strength of that correlation. So correlation just means the relationship exists. Mathematicians have defined a measure of direction and magnitude for the correlation. This is called the correlation coefficient, and the correlation coefficient is denoted by the letter R. When the points on the scatter plot all lie on a line that is not horizontal, R has a value of 1 if it has a positive slope, if it rises from left to right, and a value of -1 if it has a negative slope, if it falls from left to right. So all of our correlation coefficients will be between -1 and +1. If it's a negative correlation, the closer it is to -1, the better the fit. If it's a positive correlation, the closer it is to +1, the better the fit. So if we look at this one, this is a very strong positive relation. Do you see that all these points are really close to that line? So this R value would be close to +1. Might be like 0.98. Very close. Now, the further the points get away from a line, so let's draw in what we might consider a line of best fit. Do you see how these points are further away from that line? So this does have a positive correlation, but it is a weak positive correlation. So our correlation coefficient wouldn't be close to 1. It would be closer to 0.5. What would happen if our correlation coefficient was 0?
It would be straight.
It would just be very scattered. Good. All right, now this one shows a strong negative, so it would be close to -1, and a weak negative, so it would be closer to -0.5. Okay, what do you think about this scatter plot?
None.
It's a very weak correlation, isn't it? I don't really see much of a correlation at all. So if we don't see much of a correlation at all, we would say our R value is probably close to what?
0.
Close to 0. All right. Down here we have a scatter plot. And since you guys have already done scatter plots, if you could take this data and graph it on the graph below, then start thinking about your scatter plot in terms of, is there a linear correlation? If there is it strong? Is it weak? Is it positive? Is it negative? And then we're going to use that information to make some predictions. So on this page, please go ahead and plot that data. Okay, does yours look similar to this?
Yes.
Alright, so because this is going as the latitude increases, the annual temperature is decreasing, we see a negative correlation here. Does it look strong or weak? Really strong. Strong negative correlation. So it's probably pretty close to -1. And we could draw in what we think is a good line of best fit. Okay? And so once we do that, we could use this line of best fit to answer questions like, that's not what I wanted to do. We'll change it. We'll answer different questions. Huh. There we go. So we could answer, what do you think a latitude of 40 degrees, the temperature would be? Okay, so we would come up to 40 and read on over, so a little bit under 60. So we'd say about maybe 58 degrees Fahrenheit, about 60. So you could make predictions by drawing in a line of best fit. Now, is there another way to come up with something here other than just sketching in? What do you think? We could take two of the data points we are given that look like they're really close to making a line, like two that are kind of in the middle, like this point right here and this point right here, and find the equation that goes through those two.
Wait.
How can you find the equation that passes through 2 points?
Find slope.
Find the slope, and then use point slope.
Can't you just use any point?
Can you use any?
Yeah.
You wouldn't want to pick the values that are further away from the rest. You'd want to kind of pick the ones that are in the middle. Yeah. All right. So that's one thing when we can do with our data, especially when we see it makes a strong relationship. If it's not strong, then our predictions could be way off. But this is pretty strong. So we could expect this to be close to accurate. All right, the next part of the lesson deals with causation versus correlation. And we could do all these, but we don't need to. Did it start over? There we go. Okay, we've been talking about correlation. So what does correlation mean? That it's correlated, that a relationship exists. Does correlation imply causation? Because I can show that two things are correlated, does that mean that one causes the other to happen?
Yeah.
You think?
Kind of.
Okay, well let's think about it. When in a Gallup poll, surveyors asked her, do you believe that correlation implies causation? Well, 64% of America said yes. And we had kind of a mixed reaction here. 38% said no. And 8% were undecided.
Actually, it doesn't necessarily mean causation, but it implies causation.
I don't think.
That doesn't.
That doesn't add up.
That doesn't even add up to
64.
100. We got a problem, don't we?
Maybe if it was
Statisticians in this
54%.
course, man.
Okay, so here we go. Ice cream sales are strongly correlated with crime rates. Therefore, ice cream causes crime. That's obviously true because there's a strong correlation.
Oh, I was right.
Wait, is there
Oh, I thought ice cream was like a street name for like drugs.
Oh, I
thought ice cream was a street name for drugs.
Yeah, it doesn't.
cocaine.
Ice cream goes up. When the ice cream goes up, crime goes up.
Okay, so that led to good discussion. Maybe ice cream doesn't cause crime. Maybe ice cream sales are tied to temperature, and as it warms up, more people come out of homes, and there's more activity, and therefore there might be more crime. Okay, so we have correlation. It's just a relationship between two or more things which change, and we call things that change in math variables. And we can describe those mathematically. Correlation refers to how closely two sets of information or data are related. Okay? We gave the Webster definition, but we're going to stick with mathematical. Causation is the act or process of causing. The act or agency which produces it should be an effect. So this is also referred to as the cause and effect. So, if we have a causal relationship between two things or events exist if one occurs because of the other. So, does crime occur because of ice cream? No. So there's not really causation here. Now, for example, I can say that when I work fewer hours, I earn less money. There's a direct cause and effect relationship between working a certain number of hours and earning a certain amount of money. That's obviously if you get paid by hours. With your salary, you can work as much as you want and get paid the same amount. All right. So without proper interpretation, causation should not be assumed or even implied. And with causation, we really need to have had some kind of controlled study. So, poor ice cream is getting a bad rap today. Ice cream sales and the number of shark attacks of swimmers are correlated.
Well, that actually makes sense. It's pretty bad.
Does that make sense?
Yeah.
So they get battered, so then they can't swim, so then the sharks attack them.
They eat too much ice cream. The robbers are stealing are going and robbing their homes. They get a call from their security company that a robber is raiding their home because they went and got ice cream, and while they're swimming, and then a shark comes and eats them while they're on the phone.
Wow. I was just thinking that when it warms up, you sell more ice cream, and when it warms up, more people get in the ocean, therefore...
Oh, no.
No, that's not it at all. Okay. Oh, I went too fast. Let's get to the last one. The number of cavities in elementary school children and the vocabulary size are strongly correlated.
A little bit, because as they go to school and they see the vocabulary, they're like, I don't want to do this anymore. They go, when they eat their day, they go.
Oh, because smart people have a large vocabulary, and a lot of people are smart because their parents care about their education, so then their parents also care about taking them to the dentist. But then the parents that don't care about their education don't care about taking them to the dentist.
Oh, that's true.
I would agree with you. I think that was
I would agree with that.
yeah, that was a very nice description of probably what happens here. Okay, so when can we imply causation? So once again, when a controlled experiments are performed. And these experiments may happen over and over and over again. So eventually, if enough data is found to have a very strong correlation, then we can imply causation. And with most of our data, it's a controlled experiment, so we have a controlled group, an experimental group. So at this point, we know that smoking causes cancer. But studies had to be done over and over and over and over and over to link that closely enough to indicate causation over just correlation. Okay? Alright, now, sometimes we have confounding variables that have to be eliminated before we can imply causation. So like with the ice cream and the shark attacks, there were some other variables in there. It wasn't just ice cream sales that were causing shark attacks. Our other variables would have been time of year. Heat.
Cramps in the ocean because of eating.
Maybe that would be it. Okay?
Cramps in the ocean.
Alright. So, here are some variables that are related, and they've given our correlation coefficient. So kids' TV habits tied to lower IQ scores. So as you watch TV more, you have a lower IQ. It's not a strong negative, is it? No.
How do you we're not finding exact correlation coefficients.
We are not yet. When you're given a set of data, I will show you how to use a calculator to come up with R. Yeah.
Isn't the formula really huge?
It is a huge formula, but it's not when it comes to yeah. All right. Eating pizza cuts, cancer risk.
A little bit. Well, actually, pepperoni has chemicals in it that cause cancer.
Oh, so that's our R is not very strong, is it? A strong negative relationship would be really close to what number? -1. All right. Gun bills and warding off crime.
I don't like that.
This is still not strong.
What's gun bill? Oh, gun bill. Oh.
Legislation. Legislation.
Dude.
If you look at Chicago's crime rate, I think this would make this a little closer to 0. Because they have more gun regulations and more gun crime than most large cities.
The streets aren't safe for kids anymore.
America would have like one of the lowest murder rates in the world without like the 5 cities.
Okay, reading fights cavities.
I mean, you guys Compton cities.
Hey, what you trying to say about Compton?
Okay.
No, I don't. It's a lot.
That is dangerous.
Body mass index compared to graffiti and litter.
Yeah, body mass index. Because you're a hooligan. You're a hooligan.
All right.
Usually hooligans are skinny. No, because like hooligans gotta move fast to get away from the law, and you don't want to stereotype obese people, but they can't usually move quite fast. So.
Okay.
Wait, if it's a
Here we go.
what does that mean?
As the global temperature increases, the number of pirates must be decreasing.
Yes,
Wait,
Very, very strong negative correlation.
wait, so wait, if it's a negative correlation, does that mean that they aren't very correlated, or does that mean
Negative is fine. That just means as one increases, the other decreases. And the closer to -1, the better the fit. But do any of these actually mean causation?
no?
No. Okay.
So
You need
we're
more
saying
water.
that all the people should become pirates in Somalia, and then we have this
I mentioned that in my fifth grade, and I don't know
Okay.
What would you admit?
So flip over to page 347 and read this interesting information about your brain and how you interact with others.
Wait, is this what I think? Yeah.
Yes.
Was this like what we're watching about the brain?
A lot of it. No one uses Facebook, so.
I used to have Facebook.
I still have Facebook. I've never had Facebook. I've gotten to Facebook that I wasn't allowed to have.
I had Facebook,
I never.
and I
Yes, you did.
I haven't
Did
been
I?
on it in about.
I don't know what the username or password is.
But you were friends with Miss.
Oh, yeah.
Miss Howard.
Who got
married after
who got
meeting
divorced, and then a week
Who later
later,
got
she
married.
went to Africa, and then she met his
And then she got married.
Okay, guys, it sounds like you've read it. So what are our two variables that we're looking at here?
social network and brain size.
Social network and brain size. Now this doesn't have to just be, when this is talking about social network, it might be groups of real friends, not your imaginary friends on technology devices, okay? Not how many Twitter followers you have, or it's like real human interaction. I know, it's strange, isn't it? Who does that? Yes, sir.
This whole thing isn't valid though, because in our science fair, if you're doing something with when you have humans, you're supposed to have at least 100 participants.
There's a lot of things that's wrong with this. We don't have enough people. We can't imply causation. Does it tell us we have a control group? No. It basically was an experiment where we just basically asked them, so how many friends you got? And now let's look at the size of, how do you say this? Who's good at science in here? Okay. All right, that sounds good. All right. And so guys, do we even know if the size of the social network causes the larger part of your brain? Or do we know if you were innately born with a larger part of your brain, therefore you were inclined to be more social? We don't. So we don't know which would be the independent dependent. We don't know which would be the cause and the effect, do we? So we really can't explain, we can't defend causation here. There might be a correlation, but we can't defend the causation with just the information we were given. Okay. In your workbook, we are doing these last two pages, 353, and so you're going to talk about, guys, I need you to be quiet while I explain this assignment, okay? We're going to talk about correlation, positive, negative, strong, weak. We're going to talk about, well, you're going to plot points and talk about that relationship. You're also going to plot points, draw in what you would consider a good trend line, describe the correlation, and then make predictions on that. Okay? Later on this week, we're going to learn how to take actual data in our calculator and determine what the correlation coefficient for that data is. Now, once again, we know a strong correlation coefficient will either be very close to +1 or very close to -1. A strong correlation coefficient indicates that a linear function is a good model. Okay? So you're doing page 353 and 354, and you have 5 minutes left. You might can finish.
I already did it.
Oh,
Hey,
yeah.
hey guys, I finished.
We got